Here we see another useful standard result, that is the integral of the form e raised to x multiplied by f of x plus f dash of x is given by e raised to x into f of x plus c. So that means, suppose if we see the integral in which there is e raised to x term is present and that is multiplied by the sum of some function and its derivative. Alright, so if this is the pattern, then the answer is straight away e raised to x into that particular function. Now this is very easy to verify, because if we differentiate the right hand side, then we will get the expression which is inside the integration. So that is, suppose we want to differentiate e raised to x, so that is nothing but by product rule e raised to x as it is into derivative of the second function, correct, plus second function as it is into derivative of first function, which is nothing but e raised to x. So taking e raised to x common from both the terms, we get precisely the expression which is inside the integral on left hand side. So the idea here is to spot some function f of x and its derivative, and we have to keep in mind that they must be connected by the plus sign, that is, it must be added. Right? Now of course we can easily solve the question in which it is directly given as f of x and f dash of x. So let us see slightly different tricky questions in which it is not that evident. Here we see that we have to integrate e raised to x sec x into 1 plus tan x. Now here, comparing with the standard form, we must have e raised to x as the term outside, and the function and derivative has to be adjusted inside. So suppose we multiply the terms inside the bracket by sec x, we will get sec x plus sec x tan x, right? And now the pattern becomes immediately apparent, that is, if we call sec x as the function, then its derivative is nothing but sec x into tan x, which is automatically present. So therefore the answer of this is e raised to x into the function which is sec x plus c. Right? So that's the way we use this particular form. Let's solve few more questions which are based on this, but they are slightly twisted. Now here we have integral of x into e raised to x upon x plus 1 the whole square. Now here it's not readily apparent, that is, which is the function and which is the derivative. So let us slowly separate the terms, that is, let's write e raised to x separately, and inside let us write the remaining function, that is x upon x plus 1 the whole square. Alright. Now here we use a little trick, that is, we observe that in the denominator we have x plus 1 squared, and in the numerator we have just x. So what is missing? It is 1, isn't it? So therefore we add and subtract 1 in the numerator, right? So writing denominator as it is, that is x plus 1 the whole square. Now see what happens if we split the two terms inside the bracket. So the first term is x plus 1 upon x plus 1 the whole square. So cancelling x plus 1, we are left with just 1 upon x plus 1 and minus 1 upon x plus 1 the whole square with respect to x. And now we can immediately spot, that is, the first term 1 upon x plus 1 has to be considered as the function, because its derivative is nothing but minus 1 upon x plus 1 the whole square, as we can easily see. So therefore the answer is nothing but e raised to x into the function which is 1 upon x plus 1. So it is e raised to x upon x plus 1 plus c. That's the final answer. Okay. Let's go ahead and see one more question. Now this is even more twisted. We have to integrate 1 upon log x minus 1 upon log x the whole square. Now here interesting thing is there is no e raised to x term, right, which is what we expect if you want to use that particular standard result that we saw. So if it is not present, then how can we bring it if it is not readily apparent? We observe that we are given log, so we can't resist noting the connection between log and e raised to x. They are just the opposite processes. So what if we substitute log x with another variable t? So if log of x is t, then it means x is nothing but e raised to t, isn't it? So we are precisely substituting x with e raised to t. So on differentiation we get dx is nothing but e raised to t dt, isn't it? So putting that in the integral, we get integral of 1 upon log x is 1 upon t minus 1 upon log x the whole squared is minus 1 upon t square into dx is nothing but e raised to t dt. And now immediately once again the required form appears. So if we consider 1 upon t as the function, then its derivative is minus 1 upon t square, and we have the e raised to t as expected. So therefore the answer of this result is e raised to t upon t plus c. And at the end we must put the terms back in x because t is the substitution variable that we added on our own. So e raised to t is nothing but x divided by t is nothing but log x plus c. So that's the final answer.